Hello, everyone. Welcome back to day two. Today we start with the second part of the inference class. Let me emphasize one more time. The main thing of this lecture is to learn and understand the likely function better and see how widely this likely function is used in many fields of statistical inference. So likely function is a joint probability density function of the observed data or joint probability mass function of the observed data. But we consider this probability density or mass function as a function of the parameter given the fixed data. This is the definition, but astronomers sometimes make the mistake in terms of notation. It's not completely wrong mistake, completely wrong thing. But one example I found is from this paper published in 2020 in Nature Communications, titled Gravitational Wave Astroseismology with Fundamental Modes from Compact Binary Inspired. So if you see this paper, especially for the methodology part on page 5, so here I want to emphasize that, okay, they are considering the likelihood as a function of the data given the fixed parameter. Definitely, this is a wrong interpretation of the likelihood function, but we can also think of this as some mistake in notation, I think. But definitely every statistician will stop here and think about the meaning of this phrase, and probably they will let it go because this is some notational issue. But definitely this is something that makes statisticians uncomfortable. Another example, published in 2019, this is about gravitational wave of the A LIGO. If you see page 5, then there is another issue here. So they are talking about likelihood function, but they are thinking of the function as this likelihood as a function of data given parameters. Definitely, this is a place where statisticians will stop and rethink of this phrase. Of course, they will let it go, but in the end, this is something that makes statisticians uncomfortable. Since you just learned what the likelihood function is, I hope you use some correct phrase or expression of the likelihood function. One more time, likelihood function is a joint probability density function considered as a function of the parameter given the fixed data. Just want to emphasize that one more time before I move on. Last time I talked about likelihood function, and then we are moving on to interval estimation. Again, you will see how likelihood function works in terms of deriving the confidence interval estimation. So the reason we derive the interval estimation is to give some field of, say, margin of error around the point estimate. Because if I just give you a point estimate, you might be wondering how uncertain that point estimate is, the single number is. So we typically give some range of some likely values of the parameter values. So let's talk about confidence interval, which is a main tool for frequentist statistical inference. We typically fix some constant alpha, which is called confidence level. Confidence level is basically 1 minus alpha, sorry. In statistics, we typically fix alpha at 0.05 because we like to derive 95% confidence interval. But in astronomy, people use alpha equal to 0.32 because basically this is 68% confidence interval. For 68% confidence interval. The reason is that astronomers are familiar with giving some point estimate plus minus some single standard error, which is about 68.3% the interval. It can be Bayesian or it can be frequentist, but that is 68.3% 3% interval. But for this lecture, I will use alpha equal to 0.05, and all the contents will be about deriving 95% confidence interval. And let me define a 95 confidence interval. And that interval is a random interval with lower bound and upper bound, such that the probability that this random interval contains the unknown theta, and that probability is 0.95. One thing is very unique here, and there are many mistakes around the interpretation of this probability. The key is to think of where the randomness comes from. From frequency's point of view, the theta, the parameter of interest, is a fixed constant, which is just unknown fixed constant, but it's not random thing. The randomness of confidence interval comes from the realizations of the data, these X parts. Because the randomness comes from the data, the interpretation becomes pretty unique. For example, the actual confidence interval that we calculate from the data is just one possible interval out of so many possible realizations of the data, of the intervals coming from so many possible realizations of the data. So we call this interval a confidence interval. It's not the confidence interval. So that's one thing I want to mention. And as for the interpretation, because the data are the source of the randomness in a 95 confidence interval, we cannot say that the theta, the unknown parameter theta, is within the interval with 95% chance. We cannot interpret the confidence interval, a confidence interval, in this way. If you like to if you want to have an interval with such an interpretation, you need to move on to a Bayesian credible interval. This is exactly the interpretation of a Bayesian credible interval, which we don't cover in this class, but Tom Roletto will cover it tomorrow, the day after tomorrow, or credible interval. Interval. Instead, because the source of randomness comes from the data, it has very unique interpretation. And let me tell you this. So the interpretation is basically based on a repeated experiment, some hypothetical experimental, hypothetical repetition of the same experiment under the same condition. For example, if we could obtain the data set, a random sample, repeatedly, for example, 100 times under the same condition, which is unrealistic, but let's assume that it was possible to obtain 100 data sets obtained from the same condition. And we compute a confidence interval for each data set. And the interpretation of that interval is that the 95% of those intervals, for example, in this case, 95 confidence intervals are expected to contain the parameter out of 100% confidence interval. So what I'm saying is that if you repeatedly obtain, if it is possible to obtain the data repeatedly, and we calculate the confidence interval for each data set, then we expect that 95% of those confidence intervals are expected to contain the parameter. For example, in this figure, theta is fixed at a horizontal value. Some value at the horizontal line is fixed, it's not random. But randomness comes from the realization of data. So for the first data set, we probably could calculate confidence interval 1 from the data 1. And probably we could calculate confidence interval 2 from another realization of the data. because we assume that we could repeat the data generation process, and et cetera, until confidence interval 20. So if we calculate 20 intervals by repeatedly sampling the data 20 times, 1 out of 20 may not contain the theta, which is expected. May not contain theta. And one thing I want to emphasize is that in practice, we cannot actually get these 20 intervals. We only have one data set and we only calculate one interval. So in practice, just in reality, just one of these intervals is what we actually get from the data. Because the interpretation assumes some hypothetical repetition of experiments. Interpretation is based on that hypothetical scenario, but in reality, just one of these 20 interval is what we actually compute from the realization of the data. So, example, essentially, deriving a confidence interval start with the MLE. So in principle, I forgot to write down this. I should have done, but sorry about that. A confidence interval is derived from the distribution of the MLE. Estimator, but in many cases, it will be MLE. In the example of luminosity function for clusters in Milky Way, which was in VDB 1985, sigma is completely known as 1.2 magnitude. And given a random sample of globular clusters, we assume that the data are coming from a Gaussian population with unknown center mu with the known variance sigma square. In this case, what is a 95% confidence interval for mu? We already know that the MLE for mu on the Gaussian population is sample mean. So MLE for the mu is sample mean. And since the data are coming from Gaussian distribution center at mu with variance sigma square, the distribution of sample mean is another Gaussian distribution with the same mean, but the variance is sigma square over n. Because each data, by the way, this notation, 3 dots, 3 flip triangle dot, 3 dots in a flip triangle is because each data point is coming from normal distribution center at mu with variance sigma square. So this is equivalent to say the standardized form, standardized sample mean, subtracted by the mean divided by standard deviation is following a standard normal distribution. Center at 0 with variance 1, because we standardized it. So this is where we start. We typically call the standardized estimator as Z. And based on the property of Gaussian distribution, to get the 95% confidence interval, we set 2 values at the tail. For example, here and here, 1.96 and negative 1.96, because these 2 numbers will make the central region the area here in the center part equal to 0.95. And that is a probability defined by the continuous random variable. Probability in a continuous case is defined as the area under the PDF over the range of interest. In this case, the range is between negative 1.96 and 1.96 to make the central area equal to 0.95. That is the interpretation of this equation. Probability that a standard normal random variable lying between negative 1.96 and 1.96 is 0.95. The meaning is that the area under the PDF on the range between negative 1.96 and 1.96 is 0.95%. Since Z is the same as standardized sample mean, we can replace Z with sample mean minus mu divided by sigma over square root n. I just replaced it, and I rearrange these two inequalities so that it can be an interval for the parameter of interest. I just rearrange so that the inequalities are with respect to the mu to get the bounds as a function of the data and known constants. So still, this probability will lead to 95%, not 0.95. So a 95 confidence interval is defined as those lower bound and upper bound. Specifically, it will be sample mean minus 1.96 times sigma over square root of n, and sample mean plus 1.96 sigma over square root of n. This is a 95 confidence interval for mu when sigma is a known constant. In the example, specific example, the data size was 148, and the average magnitude of the data was negative 7.1, and the sigma was known to be 1.2 magnitude. So if we plug in those numbers into this formula for a 95% confidence interval, we will exactly get a interval, a range, specific range based on the data we observe. So the interpretation is more important, I think, as for the confidence interval, because people typically think that, okay, the parameter will be inside of this interval with 95% probability. Exactly wrong. That is for the Bayesian inference, Bayesian interpretation of Bayesian credible interval. For a confidence interval, the interpretation goes like this. If we repeatedly sample the data, obtain the data, computing 95% confidence interval each time, then 95% of these intervals would contain the true parameter. This is the rigorous interpretation, and the following sentence here is a supplementary comment. So the observed interval is the negative 7.29 to negative 6.91. It's just one of these possible confidence intervals based on the random realization of the data. So again, the rigorous interpretation is based on a repeated experiment, hypothetical experiment. But the actual interval may or may not contain mu, as you have seen in this figure. Because the interval that you actually calculate might be the red one, possibly. Okay, interpretation of the confidence interval is based on some hypothetical scenario where you can repeatedly sample under the same condition. Now, let's move on to the next case. Previously, we used the following quantity, the standardized sample mean, to get a confidence interval, which was sample mean minus mu divided by its standard deviation. But there may be a problem if you don't know the value of sigma. because in the previous example, we assume that sigma is completely known. What happens if it is not known? A principle, actually this is frequentist principle. Frequentist principle. A frequentist principle in statistics is to replace any unknown quantity with its estimator. So what will be a good estimator for sigma? If the data are coming from normal distribution, we typically use sample variance as a good estimator for the population variance. Sample variance is defined as sum of square errors from each datum from sample mean divided by 1/n-1. So if we replace sigma with this sample standard deviation square root of sample variance, then the quantity will follow a t distribution with n-1 degrees of freedom. Typically, this is also called student t distribution, because the distribution was published under the author name student, because the person doesn't want to disclose his name under the policy of the company he was working on. Students t distribution. Typically, t distribution comes with degrees of freedom, and in this case, this is n-1. So t distribution, let me briefly introduce what t distribution does. So t distribution is heavy tail. That's the most important property. For example, if t distribution has 5 degrees of freedom, which is true when the sample size is 6, definitely you can see that t distribution has thicker tails. Definitely thicker tail. It's hard to write down here. T distribution definitely has a thicker tail, meaning that to get the same 95% probability, you should get a wider interval, because the peak is lower than the Gaussian distribution. As you can see here, it is lower than Gaussian distribution. So in order to get the central area equal to 0.95, you actually need to extend the range from 1.96 to minus 2.57. You should extend the range to get the same probability. By the way, 2.957 is coming from student distribution, student t distribution with 5 degrees of freedom. But if the degrees of freedom are different, then definitely you will have different range to get the same 95% probability. So the same policy will be applied to deriving a 95 confidence interval when sigma is unknown. This capital T will be replaced with the definition of standardized sample mean, with sigma replaced with sample variance. So, and then we rearrange the inequality so that it becomes an interval. I mean, so that we can have lower and upper bounds of the parameter value. So if you rearrange the inequalities, this interval here is a 95% confidence interval that you will get when sigma squared is unknown. I explained some rearranging part in the following sentence, following equation here. One specific property of t distribution is that t distribution will approach to the standard normal distribution as the degrees of freedom increase, meaning that as the data size increases, the t distribution will become the same, almost the same as the Gaussian distribution. For example, as the degrees of freedom increase, the t distribution becomes standard normal distribution. The peak gets higher and the tails become thinner. So that will give us some hint about what to do when the data size is large, especially when sigma is unknown. If the data size is large, we know that t distribution is approximating the standard normal distribution pretty well. So we can just use 1.96 instead of any other quantile values from t distribution to get a 95% confidence interval for mu. So here is a summary for the confidence interval for mu when the data are coming from a Gaussian population with unknown mean, and the cases are different according to whether sigma is known or not. And the third case is sigma square is unknown and the sample size is large. By the way, this is if this is 95% confidence interval, then this number 1 minus alpha minus 2 becomes 0.975, and this number becomes 0.975 also. So if you change the confidence level, then what changes is the quantile value q sub 0.9. Q sub 1 minus alpha over 2. And the quantile is defined as a value that makes the probability equal to that subscript. For example, if this is defined as q sub 1 minus alpha over 2, that means that this area, the area under the PDF on the range less than q sub 1 minus 2 alpha is 1 minus alpha over 2. So that is definition of quantile. But if it is 95%, this quantile becomes 1.96. Okay, sigma. If sigma is unknown, we are replacing sigma with sample standard deviation, and the quantile will be computed based on t distribution. And if data size is large, we just replace sigma to sample standard deviation, and everything will be the same as the first case in that scenario. But in many cases, data are not Gaussian in astronomy. I mean, there are many like discrete random variables like Poisson counts, although they can be approximated to Gaussian. But many data sets that you might encounter in astronomical setting, the data may not be Gaussian exactly. So then what we should do, what should we do in that case? So in that case, we use MLE. MLE is kind of panacea if the data size is large. I'm emphasizing that data size should be large. For example, if the data are coming from Gaussian, we know that MLE is sample mean for mu. And if the data are Poisson counts, then the MLE for the rate will be the sample mean again. If the data are coming from Bernoulli distribution, then the MLE for theta was sample proportion, which was also sample mean of indicators. So in non-Gaussian case, what we can do? What can we do? So in that case, we can use the asymptotic optimality of MLE to get an approximate confidence interval. I mean, this is not exact confidence interval, but if the data are not Gaussian, it is hard to derive an exact confidence interval. So in that case, we use asymptotic optimality, saying MLE, if the data size is large, MLE becomes unbiased, most efficient, and normally distributed. I mean, the perfect three properties of MLE in the optimal, in the asymptotics. And if you just standardize, as I did, like subtracting the mean divided by the standard deviation, then you will get an equivalent form, but this time it'll be approximately standard normally distributed. So the scenario is the same. We have the we have the distribution of an estimator, and we know that we could get the distribution, although this is approximate. So we can just go back to our previous setting here, for example, in the first scenario here, we can just replace Z in the middle here with the standardized MLE, which is based on the Fisher information. So from that inequality, sorry for moving too fast. So after we replace Z with standardized MLE, we rearrange the inequalities so that we can have lower and upper bounds of the parameter of interest. So that's what happens here to get this specific 100%, 100 times or minus alpha percent confidence interval. But the problem is, if you see the Fisher information here, it contains theta, but theta is unknown, meaning that we cannot calculate this Fisher information. So basically, we cannot calculate this confidence interval because the interval contains the unknown parameter theta. Then what should it do? Again, a frequentist principle in statistics is to replace any unknown quantity with its good estimator. So we just replace theta with its MLE. And this is finally this is the general formula to get a approximate confidence interval using MLE for any distribution of the data. So MLE is pretty important in deriving confidence interval as well. By the way, I didn't check the Q&A. When some article on particle physics say they found visible unique confidence, what does that mean? So they use 95% confidence level, alpha equal to 0.05. Under that confidence level, they found that something unlikely. By the way, this is also related to hypothesis testing to the next topic. So I probably can answer this better at that level because finding something new is basically through the hypothesis testing procedure. But it actually has connection to confidence interval. So at that time, I will explain it one more time. When we move angles and great experiment and much larger than one experiment, so each with different data related. So with the distribution of confidence intervals coverage towards the normal. Distribution of confidence intervals coverage. So distribution of the confidence interval coverage moves toward the normal is not sure, but one thing we can sure is that the confidence intervals coverage will approach toward the nominal confidence level you set to get the interval. For example, the center of the coverage distribution will be at 95%, 0.95 in that case. Is this statement correct then? The uncertainty in a single estimator is contributing to the uncertainty of mu s. The uncertainty in the sigma is the uncertainty in the sigma estimator is contributing to the uncertainty. Yeah, that's right. That's exactly right. So here I didn't mention that, but it says the reason in this wider range, if sigma is unknown, is to account for the uncertainty of not knowing sigma square, because we are replacing unknown sigma square with our estimate, and this estimate has also its own uncertainty. We are basically adding more uncertainty in our inference on mu. So basically that's why T distribution automatically enlarges the range to account for such additional uncertainty. That's a very good point. I think I should have made a line here to account for the additional uncertainty of non-knowing sigma square. T distribution's role is to add more uncertainty just because of this reason. Thank you. By the way, there are too many questions here, and for the rest of the question, I will get back to you after the class. Okay, hypothesis testing. So the theme of hypothesis testing is different from the previous two scenarios, point estimation, interval estimation, because in that case we were interested in the most likely value of the parameter and some range of the likely values of the parameter. But in this case, question is different. Given some two statements about the parameter, which one do the data support more? That's the question. It's not subjective here. It's objective way to choose one of the two statements about the parameter based only on the data, because we need to help the data speak more about parameter. Likelihood comes again. Likelihood plays the key role in hypothesis testing as well. And for the motivation, here is the paper for the first detection of gravitational wave in 2015, although the paper was published in 2016. Okay, I prepared this paper because it's pretty pedagogical. So I emphasize some phrases here, a function of detection statistic, for example, detection statistic. Gaussian standard deviations based on corresponding noise background. The significance of the gravitational wave 150914 is greater than 5.1 sigma and 4.6 sigma. I know that it's confusing right now, but my goal is to help you understand these phrases after you learn the lecture about hypothesis testing. So I will get back to that paper to interpret those phrases after we learn hypothesis testing. So here is one simple example, the running example. So the average brightness of specific level cluster denoted by mu, parameterized by mu, statistical model, is known to be negative 7.7 magnitude. And I feel that that may not be the case. So I want to say this is not the case. So my question is, the data strongly supporting my claim that the mu, population brightness, is not negative 7.7 magnitude. And let me introduce several notation and some terms and definition of jargons. I'm sorry about that. But statistical hypothesis is about a statement of the parameter of a population, a parameter of interest in a population. For example, in the example, I am interested in the population brightness, and that is specified in my argument, whether mu is equal to negative 7.7 or not equal to negative 7.7. So those are called statistical, typically just hypothesis. Non-hypothesis is about the status quo, specifically explaining the existing status. And alternative hypothesis is where I write down what I want to say. So typically it was known to be negative 7.7, but my argument is that it may not be. So my argument should be put into the alternative hypothesis, and the existing status should be put into the null hypothesis. Simple and composite hypothesis. Simple hypothesis only specify a single number for each parameter. For example, theta equal to 0, definitely one value. So an alternative also says theta is 3. So these are simple hypotheses. But composite hypothesis allow multiple values of the parameter or some range of values. For example, null hypothesis here says theta is less than or equal to 0, a range of possibility, and the alternative says 3 possibilities of theta. So these are composite hypotheses. In practice, simple and composite hypotheses typically are mixed up to write down your argument, basically. So the definition of one-sided and two-sided hypothesis. If alternative hypotheses are composite, meaning that it allows some range of parameter values, representing one side of the parameter space around some constant C, then we call it a one-sided test. And there are 4 examples of one-sided tests. And the reason I specify 4 is that the first 2 will lead to the same conclusion. And the last 2 also will lead to the same conclusion. Statistically, the same conclusion. So they are essentially exchangeable. And if the alternative says if the null hypothesis specify a simple value, like simple hypothesis, and if the alternative specify all the other possibilities, for example, mu equal to negative 7.7, and alternative says mu is not equal to negative 7.7. In that case, we call this setting two-sided hypothesis testing. Test statistic and rejection region. Let's say there is a statistic. As I define, a statistic is a function of the data, not a function of parameter at all. So T is some function H, and the inputs are data. And let's say R is some interval on the real line. If our decision rule is like rejecting the null hypothesis if this statistic is inside the interval R, then we typically call T as a test statistic and R as a rejection region. Because if the test statistic is in R, then we will reject the null. We call it rejection region. And finally, likelihood ratio test. So likelihood ratio test is the most fundamental theoretical background of all classical frequency hypothesis testing procedure. Let me show you another paper of gravitational wave. This is about the third gravitational wave detected in December 2015. The reason I chose this paper is that this time they specify that they are doing likelihood ratio test. Probably you may not understand this yet, but after my lecture, I hope you understand what they are actually talking about. Why this evidence indicates that they actually detected gravitational wave based on likelihood ratio test. So that's the motivation. Basically, likelihood ratio tests are pretty popular, and I found that tens of thousands of articles searched with keyword likelihood ratio test. I mean, in history, I don't know how long time I searched it, but I saw those many astronomical articles with the keyword likelihood ratio test. Okay, to understand likelihood ratio test, it is better to start with simple hypothesis. So the null hypothesis says theta is some specific value, theta naught, and alternative says theta is equal to some other value, theta 1. And we need to make a choice between these two hypotheses. So let's make it a binary decision problem. Let's make it as binary decision problem. Reject the null or we do not reject the null. If we interpret this decision rule with respect to rejection region, we can say, if the data are inside the rejection region, we will reject the null. If the data are not in the rejection region, then we will not reject the null hypothesis. So basically, constructing a hypothesis testing procedure is to define the rejection region. Once you define the rejection region, then your testing procedure is uniquely determined. So the question is, how do we choose the rejection region? That's where likelihood ratio test comes from. Starts playing the key role. So the idea is to compare likelihoods under two hypotheses. For example, there are two possibilities under two hypotheses. So what happens if the likelihood is evaluated at the value under alternative hypothesis is higher than the likelihood value evaluated at the parameter value under the null? Or equivalently, we can say likelihood at theta 1 over likelihood at theta naught is greater than 1. The same equation, right? So the meaning of this inequality is that theta 1 is more likely to have generated the data you have on your hands. So basically what it says is that likelihood likes value under the null, under alternative hypothesis, because the likelihood value evaluated at theta 1 is higher than the likelihood value evaluated at the value at theta naught, the parameter value under the null. So that's pretty important concept in all classical hypothesis testing. We are basically comparing the likelihood ratio under the possibilities in the alternative and the possibilities in the null hypothesis. The best testing procedure is consistent to this concept. The likelihood ratio test defines the rejection region as a set of the data such that the likelihood ratio is greater than some constant. I know that this form may look like mysterious at first glance, but in the end, it will be summarized into some simple inequality, like test statistic greater than some constant, or test statistic less than some constant. So it will be, in the end, simplified by rearranging the inequalities. So in the end, the rejection region will be simplified into a simple inequality. And in the most statistical inference textbook, you will see these simplified forms only, because writing down deriving those simplified inequality from likelihood ratio may be tedious. So I will just follow that tradition, but I just want to say that almost all the hypothesis testing procedures specified in statistical inference book, for example, undergraduate level statistical inference book for frequentist hypothesis testing, are all based on likelihood ratio tests or generalized likelihood ratio tests you will learn. So in order to see why this likelihood ratio test is best, we need to define what is good test. So what is good test? So in the simple hypothesis testing setting, a test is good if, when the null is true, we are less likely to reject the null. In the end, the good test, it will not reject the null if null is true. If the null is false, it's not true, then a good test is more likely to reject the null, to make the right decision. If the null is wrong, then we want to reject the null. If the null is true, then we want to keep the null. We do not reject the null. And two kinds of errors are defined on that two scenarios, two possible scenarios. So type 1 error is occurring when we reject the null when the null is true. When the null is true, we want to keep the null, but we reject the null, which is called type 1 error. Type 2 error, when the alternative is true, we do not reject the null. Although we we must have to reject the null. In that case, we do not reject the null. So we quantify the error into probability. So type 1 error rate, which is defined by alpha, is the probability of rejecting the null when the null is true. Type 2 error rate is a probability of not rejecting the null when the alternative is true. And we can characterize that using the rejection region. So if the data are in the rejection region when the null is true, then that is the probability of making the type 1 error. And if the data are not in the rejection region when the alternative is true, we are basically quantifying that as beta, the type 2 error rate. So this figure is prepared to illustrate that. For example, this distribution is the distribution when the null is true. And similarly, we define the distribution on the right. Distribution when alternative is true. And the vertical dashed line indicates the rejection rule. So in this way, we reject the null. And for the other way, we do not reject the null. So blue area, the right tail area of the left distribution is exactly indicating type 1 error rate, because this is a probability of rejecting the null when the null is true. I mean, when the null is true is represented as the distribution on the left-hand side. And the rejection region is toward the right-hand side from the dashed line. So this is probability of committing type 1 error. And the left tail area of the right-hand side distribution indicates the type 2 error rate. Probability of not rejecting the null when the alternative is true. When the alternative, the phrase "when the alternative is true" is represented by the distribution on the right-hand side, and the red area on the right tail is basically the region where the data is not in the rejection region, because it is left-hand side of the vertical dashed line. So that is some visualization of type 1 and type 2 error rates. An example, when searching for a fine signal from a noise background, for example, you can think of this as gravitational wave. Some long question, but let me get back to it here because I want to finish at least this part. So example, let's say we want to find gravitational wave. The default is that gravitational does not exist in the null hypothesis. And what we actually want to say is that we actually found gravitational wave signal. So alternative says signal exists. But type 1 error rate, type 1 error, not rate, occurs when we incorrectly say that a signal, gravitational wave signal, is present. We found the signal, although it was not actually. So a signal is present. That conclusion is from rejecting the null, although it is actually not. So type 1 error occurs in that scenario under astronomical context. So how do the error rate change with the size of rejection region? So as I said, alpha, type 1 error rate, is probability that the data in the rejection region when the null is true. And beta is probability that the data is not in the rejection region when alternative is true. So how do alpha and beta change if the size of R changes. For example, if R is large, then the data are more likely to be in the rejection region, because I mean, if the R cover most of the range on the real line, then the data will fall into that line, right? So are more likely to be in the rejection region if rejection region becomes large. That means alpha becomes larger and beta is small, because alpha is probability that the data falling into rejection region. If the rejection is large, then that probability becomes higher. The opposite happens if the rejection region becomes small, is in a very tiny region, then data are less likely to be in the rejection region, resulting in small alpha and large beta. Because if the rejection region is small, then the probability of the data falling into that small region will become smaller. Ideally, we want to minimize both error rates, but that is impossible because alpha and beta move to the opposite directions depending on the size of the rejection region. So what we do in practice is to fix one of them, fix the upper limit of one of them, and we try to minimize the other. In practice, we fix the type 1 error rate. We typically set the upper limit of type 1 error rate, and we try to minimize type 2 error rate. And the likelihood ratio test will be the best in terms of that criteria. For example, if we just interpret the Neyman-Pearson lemma, what it says is that when the hypotheses are simple, like specifying one specific value under the null and the other specific value under the alternative, and if we fix the type 1 error rate as an upper bound of type 1 error rate, then likelihood ratio test will have the smallest type 2 error rate, meaning that no other testing procedure will become better than likelihood ratio test if we fix the type 1 error rate. And then if we want to minimize the type 2 error rate, likelihood ratio test is the best under that scenario, which is specified in this famous theorem, lemma, Neyman-Pearson lemma. But what happens if the hypothesis is one-sided, not just simple hypothesis? So in that case, it turns out that the likelihood ratio test is still the best, still the most powerful testing procedure. However, as for two-sided hypothesis testing, there doesn't exist a single most powerful testing procedure in that case. What happens is we still try to control the type 1 error rate at a fixed constant, and we try to do our best to minimize type 2 error rate. So hoping that procedure performs reasonably well in terms of minimizing type 2 error rate, which is called generalized likelihood ratio test. To summarize, when it comes to simple and one-sided hypothesis testing, likelihood ratio test is the most powerful testing procedure that you want to use. When it comes to two-sided test, we use a little bit improved version of likelihood ratio test, which is called generalized likelihood ratio test. But that is known to be pretty well. Known to perform pretty well and perform better than the other arbitrary testing procedures. So that's the summary of the theory, but let's get back to the practical issue. How do we derive the likelihood ratio test? So we derive the likelihood ratio test by using the MLE. So in the likelihood ratio test, the rejection region has some likelihood ratio, but I told you that it will be simplified into some test statistic, a simple inequality related to test statistic. And in the likelihood ratio test, that test statistic will be the MLE or a function of MLE. So in a Gaussian case, the MLE was mu. MLE of mu was sample mean. In a Bernoulli case, the MLE for the proportion was sample proportion. For the Poisson case, the MLE for the rate, unknown rate, was also sample mean. And the rejection region, the direction to reject the null will be determined by the direction of the alternative. For example, I think I moved pretty fast, but let me emphasize that this testing procedure will be based on the standardized form of the MLE under the null hypothesis. I will explain that later. But in the example, let's try to find the direction of the rejection region based on the direction of the alternative. So let's find the rejection region when the null hypothesis is simple, theta equal to theta naught, but the alternative is one-sided or two-sided. In this case, we will reject the null if t is greater than some constant for the first alternative. We will reject the null if the test statistic is less than some constant for the second alternative. And we will reject the null if the absolute value of test statistic is greater than some constant for the two-sided interval. So what I want to emphasize is that the rejection direction, the direction to reject the null, will be consistent to the direction of the alternative that you are specifying. And then let's get back to a specific example. I prepare a t-test, which is one of the most famous likelihood ratio tests. In the example of VDB, we got a random sample of 148 measurements, and the sample average brightness was negative 7.5 magnitude, and the sample variance was 1.1 squared, meaning that sigma is unknown. Sigma square unknown here. And I feel that the true population brightness is not equal to negative 7.7 magnitude. And I want to test it at the significance level alpha equals 0.05. So this is related to the first question in Q&A I mentioned. So they say they found something at 95% significance level. That is equivalent to say, okay, with a significance level alpha equal to 0.05, I mean, their argument significance level, I think, well, I don't remember, but that is equivalent to saying the significance level alpha equal to 0.05 because significance level is basically type 1 error rate. And we will see the connection with their argument soon. So we set up the hypothesis. Null hypothesis says the existing status. People believe that the population brightness is equal to negative 7.7. But what I want to say based on the data is that the population brightness may not be negative 7.7 magnitude. And we set up a test statistic for mu under the null hypothesis. This is where we use the maximum likelihood estimator. So we know that the MLE for the mu was sample mean. And I told you in the interval estimation that this sample mean follows normal distribution with mean mu with variance sigma squared over n. And then we standardize the sample mean so that we can have standard normal distribution. Standardize subtracting mean divided by standard deviation, and we know that this is now standard normal. And then we replace the unknown quantity sigma with the estimate. So it'll be sample mean minus mu over sample standard deviation divided by square root of n, and now it is t distribution with n minus 1 degrees of freedom. And finally, we replace mu with mu naught. negative 7.7, the value under the null, because we want to have some quantity under the null, and we want to find the distribution under the null. So if we replace that, it will be sample mean minus mu naught, which is negative 7.7 over sample standard deviation of square root 10. And now this is again T distribution, but this time it is under the null hypothesis, meaning that the value of negative 7.7 is true, and if the true brightness is negative 7.7, the test statistic, the final test statistic, which is T, defined by T, will follow T distribution with n-1 degrees of freedom. Okay, because we only derive that, we know that this should be under the null, T distribution with n-1 degrees of freedom. Because the data size is pretty large, we can also say that this is approximately same as standard normal distribution. So we will use the same quantile values. That makes the both tail areas equal to, some of the tail areas on the left and right equal to negative 0.05, because we are concerned about significance level alpha equal to 0.05. Specific value will be 0.025, which is alpha over 2, and the same value for the area, 0.025, which is equal to alpha over 2. So if you add the two tail areas, it will be equal to the significance level alpha equal to 0.05. So we will reject the null. Basically, I also need to say that I need to visualize that into this part, which will be here, negative 1.96, and it will be 1.96. And we determine the rejection rule based on that distribution. So we will reject the null if the test statistic lies in the rejection region, and in the complement area, we will not reject the null. If the test statistic under the null falls in this area, we do not reject the null. But if the test statistic is lying in the rejection region, then we will reject the null. And to determine that, we need to calculate the specific value of the test statistic. So I enter all the numbers given in the problem to get this 2.21. And this 2.21 lies in the rejection region, outside of the range between negative 1.96 and 1.96, meaning that something very unlikely happened. Something very unlikely happened. If the null was true, were true. Because the test statistic lies in the area where the probability is just very small number, like 0.05. 1 out of 20 cases, it will happen, but that actually happened based on the test statistics. So we reject we make a conclusion that we reject the null, and we report the statistical significance between the population mean, the known population mean, and the hypothesized value equal to negative 7.7. That's the t-test for one sample t-test. There are two other ways to conduct the same hypothesis testing, and the first one is exactly related to the first question. So hypothesis testing by confidence interval. We can actually do the same hypothesis testing by deriving a confidence interval with the same significance level and see whether the hypothesized value under the null is inside the interval. For example, in the same example, I derive a 95 confidence interval using the scenario 3 and the interval estimation. Because the sample size is large, it'll be sample mean plus minus 1.96 times sample standard deviation divided by square root of n. And I calculated this confidence interval, and I checked whether negative 7.7, the hypothesized value under the null, is inside this interval or not. This 95% confidence interval for mu doesn't contain the hypothesized value under the null. And so our conclusion is that at the 5% significance level, we reject the null. And the decision will be consistent whether you derive rejection region, compute the test statistic, or whether you just calculate a confidence interval to reject the null hypothesis. I think this is what the first question actually handles in the paper, where they're arguing that, oh, we found something. Hypothesis testing by p-value is the second one, and p-value, which is a big source for misunderstanding, is defined as this. So p-value is defined as probability of observing the current test statistic or more extreme one. So it means that under the distribution of the test statistic that we saw above, we actually observed the specific value small t, which was equal to negative 2.21. The observed test statistic was 2.21, and the p-value is the probability of observing more extreme one. So it'll be more extreme area, toward the direction of the rejecting the null, and negative t, because this is two-sided. So that's why p-value in this two-sided hypothesis testing can be simplified by 2 times one-tail area, basically. Because this is, in this case, the test statistic is symmetric around 0. For instance, when I calculate the p-value in the VDB example, the p-value was 0.033. That was smaller than the significance level. So at the 5% significance level, we conclude that we have enough evidence in the data to reject the null. So one biggest misunderstanding around p-value is that p-value is not the probability that the null is correct. It's actually the probability of observing more extreme test statistic than the current one. So please be careful about the interpretation of the p-value. And I think this is the time for 2 minutes. Let me go through model comparison. So there are some cases where we want to compare the two models. Which one is better to explain the data? We can also use likelihood ratio tests. One is a likelihood under one model, and the other is likelihood on the other model. But the problem is that likelihood ratio test is limited by 2 disadvantages. Likelihood ratio test can only compare a nested models, meaning that one model is a simplified version of the other. And also, the problem of likelihood ratio is that if the model gets complicated, if it has more parameter, if one model has more parameter than the others, then the likelihood is always bigger than the other likelihood, no matter how useful, how useless parameters are in the model. So we basically need to penalize that adding useless parameters into the model. That's why we use AIC and BIC. Basically, this is a composite measure of goodness of fit evaluated by the likelihood, and we penalize the model complexity by adding some constant proportional to the number of parameters. So what I want to emphasize, and BIC, let me go through quickly in 2 minutes, sorry about that. So BIC is the same as the AIC, except that it has stronger penalty for the model complexity. So log of n, ln basically, will be greater than 2, which is from AIC, if the data size is greater than or equal to 8. So in many cases, with reasonable size of the data, BIC will prefer more parsimonious models than AIC does. So here is an example. I can go over this in 1 minute. So here is an example of Hubble constant estimation in the original paper of Hubble in 1929. I just displayed the data listed in the paper, and there are 4 possible models. For example, the velocity is some linear function of distance, a linear function of distance, or a velocity doesn't depend on distance in model 2, and velocity only depends on the distance with no intercept, and model 4 specify that velocity is determined no matter what, by random. And I calculate the AIC and BIC for these 4 models, and it turns out that model 3 has the smallest value of AIC and BIC. So it seems like the data are telling us that, oh, I like model 3 based with respect to AIC and BIC. And that conclusion is actually consistent to Hubble's argument, because Hubble's argument in the paper is that velocity is some slope times distance without any intercept term in a linear regression. And that slope is interpreted as the Hubble constant. By the way, I'm so sorry for spending 2 more minutes, and I'm so sorry for proceeding pretty fast. But I will try to supplement this annotated version, and I will upload this on the web page. Thank you very much for listening, and I will get back to those Q&As just during the break. Thank you.
Hi, thank you.